Okay, and I'm going to do the quiz from last week. So it's an electron going around a proton. I will put the text to the quiz in the description, so go ahead and check that out real quick. But in part A, we want to know if the electron moves in the xy plane in a circle of radius r, what is the angular momentum about the origin? Okay, so a few things to start off. We have here our picture with the proton in the middle, the electron up top, and we have a nice polar coordinate system to describe this motion for this electron going around the proton in a circle of radius r. Okay, and from the free body diagram here, the force is going to be radial because it's a pure attraction between these two. So the force acts along the line that connects the two charged particles. Okay? And we can write this force in terms of the unit vector IR like that. But in order to get it totally correct, we need to include a minus sign because the force is pulling inward. It's pulling inward on this electron, hence attracting it. Okay, so let's get to it. We have to find the angular momentum about the origin, so let's be as direct as possible. Angular momentum about the origin is the vector r that points from the origin to where the particle is located times p, where p is equal to mv. Now let's go ahead and write r and p in polar coordinates. R is equal to RIR, p is equal to mass times velocity, so the radial velocity and the theta velocity. Now taking this cross product, if you remember quickly, we can distribute this term over these next two terms as if it were multiplication. So it looks like this. Let me just do this briefly. I don't want to spend a whole lot of time on this. First term will be r times m times IR cross IR plus, I'm sorry, I missed the whole term there. Right, we need to multiply that by VR. So let's go ahead and do that. And then you add the other term, which is going to be r, m, v theta, IR cross I theta. And as we discussed in recitation, IR cross I theta is IZ, and IR cross IR is the zero vector. So we get, I'm just going to rearrange the scale as mr v theta IZ. In polar coordinates, v theta is equal to r omega, as we see from our derivation. So this is equal to m r squared omega Iz. That's what L is equal to. Alright? So to get the angular momentum, which points in the z direction, well, where's the z direction? The z direction is defined so that IR cross I theta gives Iz. By the right-hand rule, Iz must point out this way. Let's put Iz here. Okay. So out of the page here. Okay, so in order to know the angular momentum, well, r is equal to capital R. We know that. But omega we don't know. Okay, so how can we get it? Well, let's use what we know about the force to see if we can get omega. Right? Well, F, this is the radial force, is equal to m AR IR. FR, the sum of the forces in the r direction, the sum of the forces r components, is equal to MAR. That's what that equation says. We know from our derivation that AR is equal to d2r dt twice, so the second derivative of r, minus r omega squared. This is 0 because we're in circular motion. R is a constant capital R, so two time derivatives of it will certainly give us 0. AR is equal to negative r omega squared, right? But we know that FR is equal to MAR from this equation. So we can say negative gamma Q1, Q2 divided by capital R squared is equal to MAR, negative MR omega squared. So from here, we can get omega. Just doing this briefly, I haven't done this problem yet. Omega is equal to a big thing to the 1/2. So let's write something to the 1/2. Okay. We're going to divide by mass. We're going to divide by r, increasing the r in the denominator to r cubed. So we get gamma m, we divide by mass. Gamma q1 q2 divided by mr cubed to the 1/2 gives us omega. Now we know omega, so let's circle that. And we've already determined the angular momentum in terms of omega, so we don't have to plug it in. Okay, did I get that right? Looks like I did. Okay. Part B. Part B is, if instead of moving in a circle, the electron's position is given by r of t equals r0 plus c1t, and theta of t is given by theta 0 plus c2t. Okay? C1 and C2 are known, as well as theta 0. Okay? R0 is also known. What would be the kinetic energy of the electron? Kinetic energy is equal to 1/2 mv squared. Let's write v in polar coordinates since this is a polar problem. V is equal to dr over dt IR plus r omega I theta. So we need each of these terms because this calls for v squared. Well, if we take the magnitude of this vector v, it's equal to the r component plus the theta component, sum of each of those squares. Okay, that gives you the magnitude squared. Just like a vector in Cartesian coordinates, right? We have a vector A, which has components ax and ay. A squared, the magnitude of a squared, is equal to ax squared plus ay squared. Same thing in polar. You have a vector v, which has an r and a theta component. The magnitude of the vector squared is equal to the r component squared plus the theta component squared. Okay, so we have v squared, which is what we're looking for, is vr squared. Vr is the r component of ir, okay? So we need this first derivative of r with respect to time, and we need to square it. Plus v theta, which is the coefficient of I theta, squared. That's going to be r squared times omega squared. All right. Now each of these are evaluated at any time t, I suppose, right? We're finding the kinetic energy here as a function of time. So what we need to do is take the derivative of r with respect to time. So let's just go up here and do that. The derivative of r with respect to time, just looking to the left here, r0 is a constant, c1 is a constant, so we get c1. We need omega, and omega is equal to the derivative of theta with respect to time. Theta, given here, we have a constant plus c2t, and the derivative of theta with respect to time is c2. All right? And that's all we need. So let's plug the results in here. We have v squared is equal to c1 squared, dr over dt squared, plus, and then r is given by this function, okay? R of t. So we need to write r of 0 plus c1t squared. Omega squared is given by this result here, c2 squared. That's v squared. K is just 1/2 times m times this. And I'm not even going to write it again, right? Just copy and paste it real briefly. And that's it, okay? So, simple calculation. If we write v in polar coordinates, why did we do that? Well, because they gave us r as a function of time and theta as a function of time. It doesn't get any better than that in polar coordinates. In fact, if you know those two things, and you have motion in a plane, so your z-coordinate doesn't change, right? So this is the circular motion in a constant plane. You know r is a function of time, theta is a function of time. Well, in this case, it's not circular motion, but in polar coordinates, we can describe it with these two given functions, okay? That's as good as you get. You can get anything you want, all right? So we just wrote velocity in polar coordinates, took 1/2 mv squared, and there we go. Okay, now the last part, part C. Part C says, calculate the work done by the force exerted by the proton if the electron moves from r is equal to big R at theta equal to 0 to the point r is equal to 2 times big R at theta equal to pi over 4. Okay, so the work done between 2 points. So we're going from, let's write the r component for first, r0, where 0 is theta equal to 0. We're going to 2r pi over 4. So we're just using the notation like r theta like that to denote our points in polar coordinates. The work done there is equal to the integral of the net force, so it's the total force. Remember, the work energy theorem says to take total force. In this case, we're just doing the work done by the force exerted. Well, here the total force is that. We're not really using even the work energy theorem. We're just calculating work. Okay, so excuse me for saying that. But we're going from the initial point, which is r0, to the final point, which is going to be 2r pi over 4. Pi over 4. So, that first thing we need is f in polar coordinates, but we also need dr in polar coordinates. So, from up here, f in polar coordinates is given by this. So let's copy it, and let's bring it down. Okay? Alright. So f in polar coordinates, we'll start at the next page here, is equal to this. Here we go. Now dr in polar we actually get from the velocity vector. It's a little trick. dr over dt, which is velocity, is equal to dr over dt ir, and then write omega as d theta over dt. That's the trick here. R times d theta over dt I theta. Alright, and now what you do is multiply both sides by the differential dt. Okay, so we'll get dr over dt all times dt. And by definition of differentials, which are defined in pairs, right, this first term is actually just going to be dr. You can think of it like the dt up here canceling the dt in the denominator, but we know that's not what's actually going on. That's actually how you define the vector dr, right, in terms of time. Okay, then we get dr over dt. So we get this other r, which is the polar coordinate r, not quite the same as this position function r. So I put a little underline in this position function r. If you notice, that's why I've been doing that. Okay, it's not the same as that polar coordinate r. ir plus r d theta dt dt times dt I theta. All right, this first term is just dr. This first term on the right-hand side is just going to be dr, which is the polar coordinate r, not the position r, ir. And the second term here is going to be r times d theta I theta. Okay? So let's first just take f dot dr. Here's f, here's dr. We take the dot product. ir dot ir is 1. I theta dot ir dot I theta is going to be 0. Okay? So let's show that real quick. Negative gamma q1 q2 r squared ir dot with dr ir r d theta I theta. So we distribute the dot, we distribute this term over the dot to each term in the sum. Okay? So this is equal to, and then I'm always going to have a factor of this, so I'll write it out in the front. Okay? And then we're going to get dr times ir dot ir here plus r d theta ir dot I theta. Okay. ir dot I theta is 0, so this term does not matter. All that matters is this term, and ir dot ir is 1. So, f dot dr, sorry, mistake, this should say f dot dr. I apologize, that must have been extremely confusing. Okay. F dot dr is equal to negative gamma q1 q2 all divided by r squared dr. Okay. So now to get the work, and I already put the points up above, so I'll just call them points 1 and 2. We're integrating just over the r coordinate here. So if we do need to evaluate the theta coordinate, we'll put that just in case, but really all that matters is the r in this situation. So we're going from r0 r is equal to r, theta is equal to 0, so 2r pi over 4. And that theta coordinate does not matter for this problem. Gamma, q1, q2, gamma, q1, q2. And since I'm integrating with respect to r, I'm going to write that r squared in the denominator is r to the minus 2, so I don't mess up the integration, which is what I always do. And that's equal to, so we integrate, increase the power by 1, divide by the new power. The new power is going to be negative 1. Gamma, q1, q2, r to the minus 1, evaluated. And just these r terms will matter since we don't have a theta appearing. Okay, and the work done is equal to gamma q1, q2, and then we have 1 over 2r minus 1 over r, which is equal to gamma q1, q2, 1 over 2r minus 1 over r. Well, let's write this as a 2. We multiply by 2 the numerator and denominator. Just a tricky way of multiplying by 1. Okay, and now we have 1 minus 2 on the numerator, so that gives us a negative 1 over 2r, so negative r. Okay, and that's the work done. So we have negative work done by this electric attraction force when r increases its radius. So this proton increases its radius, right? And so it didn't matter if we change the angle because the force was a radial force. It won't do any work if we change the angle. But when we changed it from r to 2r, right, that is going to affect the amount of work done. Okay, sorry about the long video. Hope you enjoyed. Hope it helped. Goodbye.